Now, this prime apartment block, downtown San Francisco, has been subject to so much media attention, negative publicity, litigation, and even calls for it to be torn down. If you would like to have an in-depth engineering understanding of what has gone wrong, then please stick with this video. You'll understand a great deal more afterwards. Good afternoon, Dr. Bill the engineer here, doing one of my occasional videos on engineering topics which are of interest to me and currently in the news. And today I want to talk about what's sometimes called the Leaning Tower of San Francisco, and that's the Millennium Tower, a 58-story residential building which has had foundation subsidence. Now, my background, I spent more than 4 decades in the offshore oil and gas industry, and there you need to design structures which are incredibly strong and very reliable. And this is due to the enormous environmental forces they need to resist. Now, you might well ask yourselves why I'm doing yet another video on the Millennium Tower when there's so many out there already. And the reason is I'm not satisfied with any of them actually. There's obviously the more sensational type of video, and these are often full of half-truths or distorted presentation of the facts, and they've provoked in some cases very strong reactions up to almost what I'd call hysteria. And obviously these I discount completely. But then there's more serious videos, in some cases prepared by qualified architects and engineers, and I somehow feel that none of them has really got to the bottom of what really went on, or maybe they've only captured part of the truth. Anyhow, please stick with this video to the end and see what my conclusions are, and I think you may well find you've got a rather different opinion on this project at the end of the day. I show here a Google Earth image of the site in question, and in the middle we've got the Millennium Tower. It used to be the tallest building in the area, but it's since been overtaken by others, and in particular by the Salesforce Tower, which is in the foreground. Now, what's not so obvious is that there's a large subsurface development, and this was the Transbay Transportation Centre, and it's a large underground rail junction and associated development. And this involved deep excavations right next to the Millennium Tower. Now, the Millennium Tower was designed by a local firm of structural engineers, Decimoni Consulting Engineers, and the geotechnical consultant was a firm called Treadwell and Rollo. Now, I show here a subsurface profile produced by Treadwell and Rollo, and this is based on borings taken at the construction site. And you see we've got different layers of fill, we've got sand, we've got clay. Goes down to -45 metres, and it terminates in what's called the Old Bay clay. Now, by contrast, I include another subsurface profile produced by a firm called Arups, and it goes down to -75 metres, and you see that it terminates in bedrock which underlies the whole site, and this is completely ignored in the Treadwell and Rollo report. The Millennium Tower has a single level basement 4.5 metres deep, and this sits on top of a 3 metres deep foundation raft. Now, for many buildings, foundation raft would be a perfectly acceptable foundation in its own right. However, owing to the exceptional weight of the Millennium Tower, the foundation raft is supported on driven precast piles, and there's nearly 1,000 of them distributed across the site. They go down to elevation level -24 metres, and they terminate in the dense marine sand. Now, the geotechnical consultants estimate that the settlement over the life of the building is going to be 4 to 6 inches. No details are given about how this was calculated, and you have to question whether it wasn't just a guesstimate based on rule of thumb. Now, the foundation settlement was based on an imposed bearing pressure of 2 to 6 kips per square foot, as advised by the structural engineer. However, it's come to light that this bearing pressure is actually very much on the low side, and Arups have shown that the actual bearing pressure is at least double this, which means that we can immediately double the estimated settlement to be in, say, the range 8 to 12 inches. The building was constructed during the period 2005 to 2009, and the actual average settlement at the end of the construction was around 20 centimetres, which is more than Treadwell and Rollo predicted for the whole life of the building. If you recall, that was in the range 4 to 6 inches or 10 to 15 centimetres, although, as I've already pointed out, this was based on underestimated bearing pressures. And since then, there have been other construction projects nearby, most notably the Transbay Transportation Centre, which had a deep excavation and extensive dewatering. The settlement of the Millennium Towers continued at pace, albeit more slowly, and has doubled to around 40 centimetres by 2021. And also there's some tilting which has developed over the last decade, with a maximum value of 40 centimetres to the west, again by 2021. The excessive settlement on the Millennium Tower started to attract attention and media coverage, and this in turn led to the prices of the apartments starting to fall, which caused a lot of unhappiness. And it came to a head in 2016 when litigation started, with the various stakeholders suing each other. And as you can imagine, there was a lot of dispute about the cause of the excessive settlement. The building owners, the Millennium Partners, they alleged that this was due to the deep excavation and the dewatering on the Transbay Transportation Centre. On the other hand, the Transbay Joint Powers Authority alleged that the excessive settlement was due to the inadequate foundation underneath the Millennium Tower. So what's my take on things? Well, I firstly want to start off with the facts, and I'll then give my opinion. Now, I'm going to take the facts from the documents published online on Professor Lawrence Kopp's website. I have to take these documents at face value unless there's some reason to discount them, and I haven't, of course, been able to verify any calculations or analyses. Well, the first thing we know is that back in the day, the combination of a basement raft sitting on top of driven piles was a fairly common foundation solution for high-rise buildings in San Francisco. But it has to be said that the Millennium Tower was pushing the envelope. Firstly, it was the tallest building ever constructed back then, and secondly, it was made out of reinforced concrete rather than structural steel, which made it into a very heavy building, although this fact seems to have escaped the geotechnical consultants. The second thing we know is that the settlement problems became evident early on during the construction phase. They knew they had a problem. And the last thing is the complicating factor of the surrounding future developments, and in particular the Transbay Transportation Centre. Now, these infrastructure projects take many years to plan, and the Millennium Tower engineers were certainly aware of this future development even during the design phase. The involvement for a geotechnical consultant on a project like this is a bit of a luxury. Very often the structural engineer has to do his own geotechnical engineering as well. But if you do have a specialist consultant available, his role in life is to ensure that all of the pitfalls and errors to do with foundation engineering are avoided. I think it's safe to say that that didn't happen on this project. Now, firstly, regarding the estimate of the settlement, as I've already pointed out, greatly underestimated bearing pressures were assumed. We don't know how this happened, but that was the fact. And because of that, the foundation settlements were always going to be underestimated. But secondly, the settlement calculations were never published, so no one could check how this settlement was estimated and whether it was realistic or not. And I suspect that if the calculations had been given, the basic error would have been detected much sooner. And now the pile design. Well, the consultant states that if you have 14-inch piles driven down into the dense marine sands, the loading capacity is going to be 260 kips, or just below 120 tonnes. And again, no calculations are given. We don't know what design code was used, what the factor of safety is. We don't know what geotechnical values were actually used. We've just got to take their word for it. And it's not good enough. Now, the foundations also have to resist horizontal forces, and this needs to be included in the concrete design. And these horizontal forces can obviously come from extreme environmental effects or seismic events. And what the consultants state is that if the head of the piles is displaced by ½ an inch horizontally, the resulting bending moments are going to look like this, and the structural engineers need to design against that. But where the hell did ½ an inch come from? Sounds to me like a number just plucked out of the air. The only way that you can assess what the internal forces are that the piles have to resist is to do what's called a pile structure interaction analysis. And there you analyse the building together with the foundations. And this has to be done by the structural engineer, and the role of the geotechnical consultant is to provide the soil characteristics to go into that analysis. And lastly, they don't seem to have considered the possibility of a global failure. What you can't do is you can't design the foundation pile by pile, and if one pile's stable, then you assume the whole lot is stable. And particularly when you've got closely spaced piles, which are short, they can move together and you can get what's called a global failure, sometimes called a slip circle failure. Now, this isn't just some very remote possibility which is never going to happen, and in fact the Transbay Joint Powers Authority regarded this as a real possibility, and before they started their excavations they constructed a massive buttress wall alongside the Millennium Tower at a cost of $60 million. Now, the possibility of a global failure not even mentioned in the geotechnical report. I think that's a big omission. The effect of the adjacent construction projects. Now, when the extent of the settlement problems on the Millennium Tower became evident, the building owners were very quick to sue the Transbay Joint Powers Authority, claiming that their transit centre had effectively undermined the foundations on the Millennium Tower. But the existence of this project had been known about for years, and it should have been identified in the geotechnical report as a future project risk with suggestive mitigations. But the report's completely silent on this. I think that's a massive omission. And finally, why was only one foundation solution even considered? And that's the use of the short-driven piles into the dense marine sands. Foundation settlement was always likely to be a problem on this project. You've got a very heavy building sitting on top of compressible soils, and you've got the added complication of the surrounding construction projects. And why didn't they even consider the use of large diameter piles going down to the bedrock? I have no idea. In my opinion, I think this report was a very substandard piece of work. So do I think that the major problem with this project was an inadequate geotechnical report? No, I'm sorry. I think the problems were far more fundamental than that. And in particular, I think that there was lack of any formal engineering control. And let me explain. If we take the single example of the incorrect bearing pressure being used to calculate settlements, there's any number of checks and balances which could and should have picked it up. So when you produce an engineering document, it firstly goes through single discipline checking, which is done by a qualified individual, but independently from the person who prepared the document. It then has interdiscipline checkings, so the document goes all the way around the engineering department and everyone else knows exactly what's going on. You then got design change control. So, for example, the decision to change from steel framing to reinforced concrete framing, and this would have been subject to the most detailed scrutiny by all affected parties before being approved and signed off. You then got design reviews by an outside engineering company. You then got the project risk register, where all possible project risks are identified, including excessive settlement, and then mitigations would be proposed, and the list goes on. And none of this seems to have happened. Now, a very good indication of how well controlled an engineering project is to pick up any document at random and look at the title block. Is the document numbered up in accordance with the project document numbering system? Is it clearly revisioned and the purpose of the rev clearly identified? Who prepared it on which date? Who checked it on which date? It's a very good indicator. Now, if, for example, we take a major volume of calculations on the Millennium Tower, which was submitted to the authorities for approval, and look at the title page, and there's no document number, there's no title block, there's nothing. And in normal parlance, this would be regarded as an uncontrolled document. And then if we dive into the document and look at the individual calculation sheets, and there's no signatures of any sort, we don't know who prepared it on which date and who checked it. In fact, I've looked through hundreds of pages of calculations and I haven't seen a single checking signature anywhere. I can only assume that no engineering checks were conducted. Now, companies like this just don't get to operate in the energy industry in most parts of the world. A prerequisite even to get onto a bid list is to have an externally certified ISO 9001 quality management system. And I have to say, I don't think these guys would even know what that was. Without wishing to over-dramatise it, as far as I'm concerned, this project was a disaster waiting to happen. Now, I don't think I'm going to surprise anyone by saying that by far the preferred foundation solution would be to have long piles going down to bedrock. And if this had been adopted, all of the foundation problems would have disappeared at a stroke. Now, if we go to the long piles, it's not going to be a direct replacement of one short pile for one long pile. The whole structural scheme would be quite different. So if we look at the basement plan, we see that all the major loads come down the central core and the perimeter columns. And at the moment, we've got a grid of piles across the site, and to mobilise the force in the piles in these central areas, the load has to be transmitted from the loading point to the pile through the basement slab. And this generates very high shear forces and attendant bending moments, and hence the slab has to be 10 foot deep or 3 meters deep. Now, if we go to long piles down to the bedrock, we aim to greatly reduce the number of piles and make them all rather larger capacity. And under the existing scheme, there's approximately 950 14-inch by 14-inch piles with a nominal load capacity of about 120 tonnes. And my guess is we'd probably aim for about a fifth of that number, with commensurately larger piles with a nominal load capacity maybe around 600 tonnes, and these would be concentrated under the loading point rather than distributed across the construction site. To get an idea of what the foundation plan would look like, I'm going to start drawing in some piles, and this is exactly how the design process would start, and at the moment without any calculations. And so if we take the basement plan here, divide it up into 3 zones, and in each zone we want around 60 to 65 piles of nominal capacity, 600 tonnes each. So I start with this column here, I put 6 piles underneath it and tie them together with a pile cap. And the purpose of the pile cap is to distribute the column loads amongst the 6 piles. And if I repeat the process all the way around the perimeter and double line of piles underneath the central core, and that gives me roughly the number I'm looking for. And now I join together the pile caps with ground beams, and fill in the central area here, we're going to have a suspended slab. This doesn't need to be too heavy because it doesn't have to resist any foundation loads, and probably the biggest load is going to be the external hydrostatic pressure from the groundwater. It's going to be around something like 20 inches or 500 millimeters deep. And because of the groundwater, it needs to be fully tanked. And we repeat the process for the other two zones of the basement area. Now, the form of construction of the pile would be determined by the equipment available. And if this was an offshore structure, we'd certainly use large diameter tubes of the piles, and they'd be driven to the required depth using a big piling hammer. However, the equipment available offshore is much bigger than you can use onshore. So for a building, you probably use some form of board pile. One way of doing it is you'd bore a hole to the required depth and socket it into the bedrock, and the hole would be stabilised by some form of drilling mud such as bentonite. The concrete would then be placed through what's known as a tremie, which is dropped at the bottom, and the concrete enters from the bottom, displacing the drilling fluid upwards. And for the top portion of the pile, you drop in a reinforcement cage, and that would be to resist the bending moments caused by the earthquake loadings. And this reinforcement cage would be knitted into the pile cap reinforcement. Now, this form of construction would be immensely strong, would certainly meet all of the design requirements, and I'm not quite sure that it would even be much more expensive than what was actually done in practice, and certainly much cheaper than the outturn costs. Now, I've just used the word disaster, so did I mean an engineering disaster or technical disaster? No, I didn't. I'd like to point out that there are a couple of reports out in the public domain, both of which conclude that the Millennium Tower is completely stable and that it will resist the design earthquake, or what's known as a maximum considered earthquake. I do have one or two questions about these reports. As an engineer, on the other hand, I am prepared to accept them at face value, given the experience and qualifications of the parties which produce them, and also the huge amount of investigative work which was done. Now, subsidence in itself isn't necessarily such a problem, and there are many parts of the world where levels of subsidence are much greater than in San Francisco. Most famous case being Mexico City, where the centre of the city has subsided by meters and meters over the years, dragging all buildings down with it. But the locals have learned how to live with it and how to manage any associated problems. The major problems tend not to be the stability of the building, with one or two famous exceptions, and more to do with serviceability problems, and in particular the interface between the building and its surroundings. So what sort of disaster did I mean? Well, PR disaster, reputational disaster, and obviously a financial disaster for the poor souls caught up in the middle of this. And this was also unnecessary and comes down to appalling communications. So imagine that back at the end of the design period, if the designers had said, well, the building settlements are going to be at least 12 inches, as they should have done if they'd merely used the correct building weight in their calculations, it might have raised a few eyebrows back then, but it would have been accepted. And you then get through to 2021, and the actual settlements have been 17 inches, and the narrative would have been, oh, the building settled a bit more than was predicted by nearly 50%. On the other hand, geotechnical engineering isn't an exact science, and it would have been accepted, no big deal. But since the designers said at the outset that the settlements were only going to be 6 inches, and you get through to 2021, and the narrative is that the actual settlements are 3 times what was predicted, everything's out of control, and panic sets in, and the rest is history. So let's summarise. What should have happened? The only sensible solution would be to found the building on large diameter piles going down to the bedrock. And if that had happened, all of the settlement issues would have disappeared. However, owing to a combination of very poor communications between the various parts of the project, extremely lax project controls, appalling decision making. It was decided to found the building on short driven piles going into the marine sands, and hence the high settlements were always going to happen. But even then the situation had been saved. If the project team had been open and upfront with all of the project stakeholders about what the likely settlements were going to be and what the implications of that were going to be, the hysteria could have been avoided. And as far as I'm concerned, this is an object lesson in how not to run a major engineering project.